Good morning, good afternoon, everyone. I'd like to welcome you to ARA's Webinar Wednesday program. I'm Jerry DiMaggio from ARA's Southern Delaware office. I'll be serving as your moderator for today's program. Today's program, entitled FDOT's Enhanced Hydroplaning Prediction Tool, be presented by Mateo Carvajal. Next slide, please. First thing I'd like to do is go through some housekeeping items with everybody, just 2 or 3 items. First of all, if you're experiencing an issue with the audio portion of your program and you're using your computer speakers, please try to call in on your phone. If you're continuing to experience a problem, then go to the chat, as you see lined up here, and send a message to the host. And you'll have several options on your chat screen, so make sure you're directing it to the correct person. Next slide, please. We encourage you to ask questions during the entire program, as we have throughout this series of over now 2 years of monthly webinars. We defer answering the questions to the conclusion of the technical program. You see highlighted in this slide the Q&A button. Please click on that, enter your question as best you can. It's okay, we'll paraphrase it as needed, and then send that to the host and the panelists. Next slide, please. Finally, housekeeping. If you're like to see the presentation in full screen mode, go to the top of your screen. To the immediate right, you see a pull down arrow. Click on that, choose the view option, and then choose fit the screen. Next slide, please. Now it's my pleasure to introduce today's presenter, Mr. Mateo Carvajal. Mateo is a civil engineer. He has a doctoral degree from the University of Kakuha. I mispronounced that, even though I practiced it quite a bit last night, in Colombia, South America. And then he has an MS degree from the University of Nevada at Reno in 2018. He's got some work experience both in at the University, Columbia Institute of Roads, University of Reno, where he was a graduate assistant, and he worked on a number of Nevada DOT research projects, and now currently with ARA since 2019. He worked with the Colombian version of the mechanistic empirical design model that's available through AASHTO. He's got experience with a number of NDT methods, fulling weight deflectometer, GPR, profilometer, and LCMS. So with that as an introduction, I'd like to now turn it over to my good friend, Mateo. Mateo, please.
Thank you, Jerry, and good morning or good afternoon, everyone, depending on where you are. Thank you for joining us today on this webinar entitled FDOT's Enhanced Hydroplaning Prediction Tool. And this is the outline of today's presentation. We will first begin with a brief introduction to hydroplaning, where we will discuss why it's important to address this phenomenon. And then we will discuss some of the fundamentals behind hydroplaning. We will learn how the factors affect it, and we will learn the basics of the hydroplaning prediction models. And finally, we'll see how these models are built inside the FDOT's Enhanced Prediction Tool. So let's get started with the introduction. And according to the National Highway Traffic and Safety Administration 10-year average data from 2007 to 2016, close to 6 million vehicle crashes occur in the US each year. And among these crashes, over 1.2 million are weather-related, and about a third of these crashes result in injuries. And unfortunately, around 5,000 people are killed due to these weather-related crashes every year. So what are weather-related crashes? Those are the ones that occur during adverse weather conditions such as rain, sleet, snow, fog, severe crosswinds, or any other conditions when the pavement surface is slippery because of the water, snow, or ice. So the 10-year average data of NHTSA also revealed that about 70% of the weather-related crashes occurred on wet pavement surfaces, and about 50% of them during rainfall. So It's a higher percentage compared with the snow-related accidents. So these numbers really indicate that the vast majority of these crashes happen on wet pavement or during rainfall. So the first outcome of a wet pavement surface is the reduced friction between the tire and the pavement surface because of the water acting as a lubricant. And normally, the tires are designed to push away any undesired substances such as water, rain, or snow. But under severe circumstances, this tire may encounter more water than it can push aside. And when this happens, um, it causes the tire to lift from the road surface. And this is the phenomenon that is known as hydroplaning or aquaplaning, which may occur when a layer of water builds between the wheels of the vehicle and the pavement surface. And for a vehicle to respond to the driver controlling inputs, the vehicle tires must be in contact with the pavement surface. But under hydroplaning conditions, the vehicle tires become completely separate from the pavement surface, and then the driver may lose control of the vehicle and slide until either one of those accidents that we talk about happens, or best case scenario, the vehicle slows down enough such that one or more of the tires contact the pavement and friction is regained. So that was the brief introduction. Now it's time to talk about the hydroplaning fundamentals. So what is hydroplaning? By definition, this is the condition that exists when a film of water or any other contaminant is present at the tire pavement interface, and that completely separates the tire from the pavement surface. So next time someone asks you what is hydroplaning, I want you to picture this image on your head: the pavement surface, a film of water completely separating this tire from the pavement surface. And when that happens, of course, you will lose your ability to maneuver, brake, or accelerate. Okay, so now that we understand hydroplaning, which is the phenomenon that separates the vehicle tire from the pavement surface, let's discuss the different types of hydroplaning. There are three major categories that may cause this phenomenon, and these categories are dynamic hydroplaning, viscous hydroplaning, and reverted rubber hydroplaning. So dynamic hydroplaning is the one we refer when we simply say hydroplaning. And as I just mentioned, dynamic hydroplaning occurs when this moving tire runs over a wet pavement surface with more water than it can push away, and it becomes completely separate from the pavement surface. And dynamic hydroplaning is the most frequent type of hydroplaning encountered in roadways. It usually occurs at high speeds, typically above 45 miles per hour. And this is the type of hydroplaning that we will be analyzing with the FDOT's Enhanced Hydroplaning Prediction Tool. Now, the second type of hydroplaning is the viscous hydroplaning. And viscous hydroplaning occurs on pavements with little to no microtexture. And the typical example, it's a pavement with a significant amount of bleeding, where the asphalt completely covers the pavement surface. And viscous hydroplaning can also occur, for example, on pavements that have been polished smooth by the traffic. And under viscous hydroplaning conditions, even a very thin film of water, even less than 1,000 of an inch, may separate that moving tire from the pavement because of the insufficient microtexture to break down the water film. So, in other words, but viscous hydroplaning may occur at almost any speed. The third type of hydroplaning is the reverted rubber hydroplaning. And reverted rubber hydroplaning occurs when the friction between the pavement and the tire generates excessive heat to the point where the rubber has melted, and it reverts back to its uncured state where all the threads are closed. And because of the high speed associated with the reverted rubber hydroplaning, this typically does not occur on roadways, but it does occur rarely on airport runways with high-speed aircraft, such as the one depicted here. So we saw the statistics and we saw the fundamentals. Now it's time to go over the factors that affect hydroplaning. So what affects hydroplaning, and more specifically the speed at which hydroplaning occurs? Hydroplaning is a complicated phenomenon, and it is affected by a number of factors, and these factors can be grouped into 4 categories. And these categories are the roadway and pavement geometry, where we have the surface type, if it is asphalt pavement, open graded, dense graded, if it is concrete pavement, if it's longitudinally grooved or transverse grooved. We have the route depth, because water may pond on these depressions, and the texture is really important, as well as the permeability, cross slope and grade, and some other geometry features such as the width, the curvature, and pavement depressions. Now, the second category is the environmental factors. Those are the factors that we do not have control over. And here we have the rainfall intensity and duration, and some models use the temperature as well. Now, the third category will be the driver behavior, where we have the driving speed, the driving maneuvers, and pretty much the driving skills. And the fourth category will be the vehicle condition, where we have the tire tread design and depth, we have the tire pressure, and of course the vehicle type and weight. And among these factors, the one related to the pavement and geometry are the ones that are considered to be within the highways agency, and it should be considered in the design phase or during the pavement evaluation for safety. Okay, so we saw the factors that affect hydroplaning. Now let's turn to go over the hydroplaning prediction models. So how do we predict hydroplaning speed? There are 2 major models involving the prediction of the hydroplaning speed. And the first model is the water-film thickness model, which uses a given rainfall intensity as well as some other input parameters that we will see in the next few slides. And remember when I told you the definition of hydroplaning, we have the moving tire and there is a water film in between the tire and the pavement surface. This is the model that we use to estimate how thick is that water on the pavement surface. And then the predicted water film thickness is used in turn to calculate the hydroplaning speed, which is pretty much how fast can we go before we start experiencing hydroplaning. And the hydroplaning prediction tool offers 4 different models for the water film thickness and 3 different models for the hydroplaning speed. For a total of 12 model combinations, we have the option of Galloway, United Kingdom Road Research Laboratory, the New Zealand Modified, and the paved drainage for the water film thickness. And for the hydroplaning speed, we also have the paved drainage. We have the University of South Florida and Galloway. And among these models, the Florida Department of Transportation recommends to use Galloway for the water film thickness and paved drainage for the hydroplaning speed. So here's the equation for the Galloway water film thickness, and as you see here, it is quite a complicated nonlinear equation with a few inputs such as the MTD, which stands for mean texture depth. We have L, which is the drainage path, I, which is the rainfall intensity, and S, which is the total slope. And among these inputs, the MTD and the rainfall intensity are direct inputs, and the drainage path and the total slope are what we call intermediate variables that need to be calculated from the remaining inputs. So I'm going to spend a little bit of time on this slide because it's really important that you understand this model, and I'm going to define each one of these inputs. So let's start with the main texture depth, and for this definition I want you to bring your attention to this image on the bottom left of this slide. So the MTD, mean texture depth, or MPD, mean profile depth, is the texture, and it is defined as all these irregularities on a pavement surface that deviate from a perfectly flat pavement surface. And that of course affects the friction, the water drainage between the tire and the pavement. And as can be seen on this same plot, the total water flow is the amount of water that is flowing on top of the pavement surface. But the water film thickness, which is the one that we use for the hydroplaning speed, It's defined as the amount of water measured from top of the pavement asperities. So in other words, the water film thickness, it's equal to the total flow of water minus the mean texture depth. And that is reflected in the equation. If you look back at the equation, the left part of the equation before the minus will be the total flow, and we will subtract the texture right here. And because the texture depth is subtracted from the total thickness of water, texture depth is a crucial factor for hydroplaning. And in general, the higher the texture depth, the lower the water film thickness, and the lower the potential for hydroplaning. So I'm going to say this again because this is really important. So the higher the texture, the lower the water film thickness, and the lower the potential for hydroplaning. So it is important that the pavement surface provides enough level of texture for draining the water. And as you can see here on the new pavement, we have nice texture. Whereas pavement with insufficient texture, for example, in-groove bridges or those experiencing natural loss due to the pavement age may show increased potential for hydroplaning. So that's all regarding the MTD. The rainfall intensity is just going to be the amount of water that's pouring on top of the pavement surface. And as I said previously, we have two other intermediate variables, which are the total slope and the drainage path. The total slope, S, is the slope of the pavement created because of the cross loop and the grade. And the water on the pavement surface is going to flow in the direction of this slope. And given the total slope, the drainage path is going to be the maximum length that a droplet of rain it's going to travel before exiting a particular lane. So for example, if the raindrop falls at the top right corner of this pavement, it will travel a distance equals to the drainage path before exiting this lane. And the steeper the longitudinal slope, the longer the drainage path is going to be. And again, the total slope and the drainage path are not inputs that you need to provide. Those are intermediate variables that are calculated by the FDOT's hydroplaning prediction tool. But I mean, you still need to understand why these inputs are important. And I want to spend a little bit more time on this slide to talk about the pavement width, the cross slope, and the grade. So first of all, the cross loop and the grade work together to determine the drainage path. So for example, if the pavement has a higher cross loop and lower grade, the water is going to flow more laterally towards the side of the pavement, and it's going to drain relatively quickly. On the other hand, if the pavement has a higher grade and little to no cross loop, then the water is going to flow more laterally towards the side of the pavement, and it's going to take more time to drain, and that is depicted on the drainage path number 2. So I want you to remember this pretty well, because we'll see some real world examples where we're going to see that combination of uncontrolled grade and almost no cross loop, which originates a long drainage path and subsequently an increased water flame thickness and of course an increased risk of hydroplaning. Now the pavement width is also important, because pavement width is essentially the shortest drainage path for a given lane. So in other words, if there is no grade and only cross loop, the drainage path will become equal to the pavement width. So another thing that's important to highlight is that the water is going to flow from one lane to the adjacent lane. So in this figure, for example, the water it's going to flow from the right lane to the left lane, which may end up with an increased water film thickness and may show increased potential for hydroplaning. So that was all regarding the water film thickness. Thank you for bearing with me on that long slide. But now it's time to look at the other model. Remember that I told you there are two models important in the prediction of the hydroplaning speed. One of them is the one that we just looked at, the water film thickness model. The other model is the hydroplaning speed. And similar to the water film thickness model, where the hydroplaning prediction tool offers several options, we have 3 different models. And we're going to be looking at the recommended by the department, which is the first one, the paved drainage. And again, here is another complicated nonlinear equation, and my intention is not for you to memorize this equation, but to see that once you have the waddle fin thickness and the texture, you can just plug in these variables here and calculate the hydroplaning speed, which again is how fast can we go before we start experiencing hydroplaning. All right, so here's where we at on our presentation. We saw those statistics, the crashes, and we saw the definition of hydroplaning, the different types of hydroplaning. We saw the different factors that affect this phenomenon. We look at the two important models, the waddle thickness and the hydroplaning speed model. Now it's turn to look at the FDOT's enhanced hydroplaning prediction tool. And here's a screenshot of the tool. I know it's almost impossible to read all these words in here, but my intention is not for you to read all this information, but to show you the structure of the tool. First, you have the section where you input all the information of the project. You're going to have the financial project ID, the roadway section number, you have the district, the county, you can use mileposts or stations, you can input here the direction of the traffic. Then you're gonna select the analysis options, and we're gonna see a few slides with all the analysis options that the tool has. Then you will select the models. Remember that I told you that we have 4 different models for the waddle fin thickness and 3 different models for the hydroplaning speed. So you can select them all or select the ones that you're interested in. And if you remember the different factors that affect hydroplaning, we have the pavement factors, the environmental and vehicle factors. So you will be asked to input this information. And on the same screen, you're going to have the results. So this is a macro-enabled Excel file, which is very user-friendly. It's meant to be used in 3 simple steps where you select your analysis options, you fill in the inputs, and you get the outputs. It's mostly used in the design phase, but it can also be used as a forensic investigation tool. And if you remember, the name of this presentation is FDOT's Enhanced Hydroplaning Prediction Tool. So it is enhanced because there used to be another tool. And here's a screenshot of that old hydroplaning prediction tool. It had several drawbacks, one of them being a MATLAB-based tool, and you know MATLAB requires expensive licensing, and not everyone is familiar with MATLAB, whereas the new tool is Excel-based, so Excel is for free, and a lot of people know about Excel. This tool wasn't very user-friendly or flexible. The units were not consistent, so you can see here the MTD is in millimeters, the variability is in inches, and you have the waddle thickness in inches, but once again in millimeters. So the units were not consistent. There were some mathematical bugs on some of those models. There was no check of warning or of unreasonable input value. So you could, for example, input a rainfall intensity of -1, which makes no sense, or you could end up with a negative waddle thickness, which also doesn't make sense. There was no an option for analyzing multiple lanes, so there was a workaround. Like if, for example, you wanted to analyze 2 12-foot lanes, you will input just one 24-foot lane. But the problem with that is that you cannot analyze what's the impact of having different crosstalk on those 2 lanes. Some of those variables were input using drop-down boxes, and some variables were provided without any units. There were some incorrect results for predicted water thickness and hydroplaning speeds, and it wasn't clear if all those inputs were needed for the specific models. So all those bugs and more functionality was added. The old tool only allowed you to do the basic hydroplaning analysis. Now we can do risk analysis based on the FDOT's design guidance, and we can do continuous analysis when continuous data is available, and we can also run sensitivity and probabilistic analysis, and we will be discussing all these options in the next few slides. So we will first go over the deterministic analysis option. And the deterministic analysis option is just a simple calculation of the intermediate and output variables based on a given set of known input parameters. And under the deterministic analysis options, we have the basic analysis, the risk analysis, and the continuous analysis. So let's look at the basic analysis first. And the first analysis option is the basic analysis. This is the most basic mode of hydroplaning analysis. You can use this option if you want to explore results from different waterfall thicknesses models or hydroplaning speed models. You can also use this option if you're only interested in calculating the waterfall thickness and the hydroplaning speed for a given set of inputs. And here on this screenshot, you can see some of the required pavement inputs. So you're gonna be asked for the grade, the surface type, where you can select if it is dense graded, open graded. And one of the nice things about the tool is that you're gonna have some recommended values for the texture based on several years of data collected by the Department of Transportation. You're gonna be asked for the permeability. Here is the information for the lanes where you need to input the crosslope and the pavement width. And one thing is important to highlight here is that you need to input all the lanes, including shoulders, gores, ramps, and any other part of the pavement, because remember that the drainage path and the waterfall thickness are going to be accumulated from one lane to the other. And here, unlike the risk analysis option, which we'll be looking at next, where the prediction is defaulted to Galloway for the waterfall thickness and to pave drainage for the hydroplaning speed, here on the basic analysis, you may select one or more waterfall thickness or hydroplaning speed models. And as a reminder, the hydroplaning tool offers 4 different models for the waterfall thickness prediction and 3 different models for the hydroplaning speed. And because every model is slightly different, some models may require additional inputs while others don't. And most of the time, these inputs include the environmental inputs such as the temperature, that you see here, which is only needed for the paved drainage waterfall thickness model. And the hydroplaning tool is going to display these inputs if and only if a model is selected. So if you don't see an input box for a particular input, it simply means that the input is not required for the model you selected. So in other words, if you don't see it, just then don't worry about it. And this screen shows a sample table of the results of the basic analysis. And because all 12 models were selected for this example, the 4 models for the waterfall thickness and the 3 models for the hydroplaning speed, we have all the results right here. So for each lane, we have up to 12 different combinations of hydroplaning speed. Okay, so we look at the basic analysis. Now it's time to go over the risk analysis option. And the risk analysis option is based on the FDOT's design guidance for the analysis of the hydroplaning risk using the hydroplaning tool. And the risk analysis is conducted by comparing the expected driver speed during certain rainfall events and the expected hydroplaning speed. And in accordance with the FDOT's design guidance, the analysis here is always based on the Galloway waterfall thickness model and the paved drainage hydroplaning speed models. So for projects in the design phase, this is going to be most likely the analysis to perform because the results of this analysis will help to steer decisions as far as how significant is the risk and whether the risk needs to be mitigated or not. And for the risk analysis, the predicted driver speed is estimated according to the table shown here. So for example, if we say a driver is going on the interstate at 70 miles per hour, and then we have a rain event of 2 inches per hour, we would expect that that driver is going to decrease the speed by 12 miles per hour. So in other words, if he or she was driving at 70 miles per hour, there is a rainfall event of 2 inches per hour. he or she is going to decrease the speed by 12 miles per hour, and now the predicted driver speed is going to be 58 miles per hour. And because the risk analysis is primarily conducted for high-speed facilities, it is assumed that the risk is minimal when the vehicle speed drops below 45 miles per hour. So, in other words, if you end up calculating a predicted driver speed of, for example, 38 miles per hour, you just need to remember that the minimum predicted driver speed is going to be set to 45 miles per hour. And here is a snapshot of the hydroplaning prediction tool where you will provide the pavement inputs. And this is very similar to what we saw on the deterministic analysis. You will be asked again for the longitudinal grade. For the surface type, you will have again the recommended values for the MTD or MPD, the texture values. You're going to have to input the permeability. Here you could model up to 12 lanes as well as the basic analysis, and once again remember to input all the information for shoulders, buffers, or in all the components of your pavement. And here is a sample output from the risk analysis, and the outputs include a table providing the predicted driver speed and another table that provides the predicted hydroplaning speed. And as can be seen here on this figure, if the hydroplaning speed is less than the predicted driver speed, both cells are going to be highlighted for the evaluation. So remember, the hydroplaning speed is how fast can we go before experience hydroplaning, and this is the predicted driver speed under a certain rainfall event. So in this example right here on lane 2, we are saying that you can go to 57.3 miles per hour before experiencing hydroplaning, but we expect that the drivers are going to go at 58 miles per hour, which represents that the drivers are going faster than the predicted hydroplaning speed, which represents an elevated risk of hydroplaning. Okay, so far, our inputs into the hydroplaning prediction tool were assumed to be constant. So in other words, if we use a crossslope of 2%, then the pavement was assumed to have 2% crossslope everywhere. But this is far from reality, and many of those pavement-related inputs change with the distance or the milepost or station. And on top of that, there are new technologies that allow to measure some of these inputs in a continuous manner. So those inputs are, for example, the crossslope, the grade, and the texture. So continuous analysis is the option that you want to use if you have one or more of those continuous data inputs available. And personally, this is the option that I use the most because we conduct forensic analysis, safety analysis here, and we have the multi-purpose RV vehicle, so we're able to collect this continuous data. So I'm going to show you the continuous analysis option with some real-world examples. And here's the first one. This is a section of the interstate where we saw an increased number of crashes between mileposts 16 and 17. The green dots represent the approximate location of the crashes. So we received the request from the district pavement engineer, and we sent our multi-purpose RV vehicle, which is actually an ARA profiler, to collect the continuous crossslope and grade. And here are the results of that data collection. So on the first plot, we have the crossslope on the y-axis in percent. On the right-hand side of the y-axis, we have the longitudinal grade, and all the x-axis of these plots are the mileposts. And if you remember, on the basic analysis and on the risk analysis, we assume to have a crossslope, a constant crossslope. So if we say, for example, 2% crossslope, that will be represented by a straight line here. But this is what happens in reality. The crossslope is changing with the milepost or with the distance or station. And there are some transition zones right here, and the grade is also changing. And if you remember, when I was describing the drainage paths, when we have this combination of almost zero crossslope and uncontrolled grade, we may end up with long drainage paths, like the one that are shown here. So 400 feet, that represents that that droplet of rain will have to travel 400 feet before exiting that given lane. And that, of course, is going to create increased water film thicknesses. And subsequently, the predicted hydroplaning speed is going to fall below the predicted driver speed, which is depicted by this orange bar right here. So this is the speed at which we expect the drivers to go, and this is how fast can we go before start experiencing hydroplaning. So in other words, the drivers are going faster than the speed at which you will experience hydroplaning, which will represent an elevated risk of hydroplaning. Okay, so we saw all the deterministic analysis options. Now it's time to go over the sensitivity analysis option. And the sensitivity analysis option allows you to simulate a variety of conditions. This may be useful during the pavement design phase. And in this option, you may vary one or more of the inputs, such as the rainfall intensity, the temperature, the crossflow, tide pressure, any of those variables at any desired intervals. And as an example, let's consider a situation where you have to run the deterministic analysis for 6 rainfall intensities, 4 texture values, and 2 crossflow values. So in total, you will need to make 48 deterministic analysis, but rather than running the program 48 times repeatedly, one single sensitivity analysis run can be made to get the results for all 48 scenarios. And once again, here is a screenshot of the pavement inputs. This is similar to what we have seen before for the deterministic analysis, with the difference that here you will need to input the minimum, the maximum, and the increment. So as an example, let's say that we want to analyze a rainfall intensity with a minimum of 0.5 inches per hour, maximum of 3 inches per hour, and an increment of 0.5 inches per hour. That will be equivalent to running the basic analysis 6 times for 0.5, 1, 1.5, all the way up to 3 inches per hour. And depending on the number of sensitivity runs, the sensitivity analysis may result in a very large number of outputs. So as can be seen in this figure, the sensitivity results are going to be provided in a separate Excel worksheet. And here the recommendation is for you to use the Excel standard filtering feature to sort through the desired outputs. So for example, here we have all those 6 options for the rainfall intensity, but if you are only concerned about 0.5, you may check this box and select only 0.5, and here you will see the results for the water film thickness and hydroplaning speed for the value that you just select. And the sensitivity analysis has also been used under the forensic analysis. Here's another real-world example. This is another section of the interstate where we saw an increased number of crashes, this time between the milepost 7.5 and 8.5. And we sent our multi-purpose survey vehicle to collect continuous data, and I tried to do a 3D representation of what the crosslope looks like. So we have a crosslope of 2% here, then we reach this transition zone, which will be something like here, and then we reach the problematic zone where we have the 0% crosslope, so almost no crosslope. And if you remember, once again, when I was describing the drainage pad, when we have almost 0% crosslope, what this is going to cause is long drainage paths, increased water film thicknesses, and the hydroplaning speed falling below the predicted driver speed. So in other words, the drivers will go faster than the speed at which we will experience hydroplaning. So what we did here is we changed the crosslope values to reduce this drainage pad and water film thickness, and to have this hydroplaning speed falling above the predicted driver speed. And we found out that the crosslope has to be at least 2.5% in order to meet all those requirements. All right, so we are getting towards the end of our presentation. We will go over the probabilistic analysis option now. And the probabilistic analysis option is just another variation of running the deterministic analysis multiple times. So this allows you to characterize certain or uncertainties associated with several variables such as the rainfall intensity, the pavement temperature, the axle weight. And this figure right here shows us an schematic illustration behind the concept. So the probabilistic inputs must be defined in terms of distribution. So we'll need to input the mean and the standard deviation rather than fixed value. So if you're not completely sure that your rainfall intensity is going to be 2 inches per hour, but you know it's on average 2.5 with a standard deviation of 1 inch per hour, you can input those values. And the output variables are going to be calculated from a set of randomly generated values from all those input parameters. And this is a sample input screen for the probabilistic analysis. Once again, you're going to be asked for some of the other inputs that you saw on the other analysis options. You will still need to input the surface type, the longitudinal grade, and the permeability. But this time, you're going to be asked for the average and the coefficient of variation. So the coefficient of variation is just simply the ratio between the standard deviation and the average, and this is expressed in units of percent. So as an example, if we specify a rainfall intensity with an average of 2 inches per hour and a coefficient of variation of 10%, the program is going to run the hydroplaning analysis with rainfall intensity having a normal distribution with a mean of 2 inches per hour and a standard deviation of 0.2 inches per hour. And also the results are going to be in terms of distributions here. So this slide shows a sample output screen for the probabilistic analysis. And in this example, you can see here for the lane 2, which is depicted by the orange bars, we can say that the predicted hydroplaning speed is going to be around 59 or 60 miles per hour on average, but it could be as low as 55 miles per hour and as high as 65 miles per hour. All right, so to summarize what we have learned today, dynamic hydroplaning occurs when the moving tire runs over a wet pavement surface with more water than it can push away. And when this happens, the tire becomes completely separate from the pavement surface. And dynamic hydroplaning is the most frequent type of hydroplaning on roadways. And this is the one that we refer when we simply say hydroplaning. This is a complicated phenomenon, and it is affected by a number of factors that can be mainly grouped into 4 categories, where we have the pavement and roadway geometry. Here's where we have the crossslope and the grade. Then we have the environmental conditions, we have the rainfall and the temperature for some models, have the driver behavior, pretty much the driver skills, and finally the vehicle conditions. And the hydroplaning prediction tool, it's implemented in a macro-enabled Excel spreadsheet environment, and this is very user-friendly, so you can run the analysis options, just selecting your analysis option, filling the inputs, and obtaining the results. And it can be downloaded for free at the FDOT's roadway drainage office website. And although this tool is simple to use, you still need to understand the various analysis options and the models, and that was the goal of this presentation. I hope you enjoyed this presentation. I want to give some special thanks to Mr. Young Lee, who was the principal investigator from the ARA side, and the folks from the Department of Transportation, Mr. Char Holscher and Lucy Chuban. And I thank you so much for your time, and I'll turn it over to Jerry for more information and questions. Thank you.
Okay, thank you, Mateo. Great presentation on a complicated topic that I wish the public could understand the complexities of the problems and the issues that we deal with in infrastructure and transportation in particular. We'll get into the Q&A program momentarily, but I hope everyone enjoyed today's program. If you're interested in our future webinars, you see the ARA.com webinar location where you can register and get additional information about previous programs. All of our programs are recorded and available. On April 28th, we're going to stick with the pavements theme for the next 2 months, actually, and we'll have Dr. Hasham Abdullah presenting conductive concrete heated pavement systems. Probably not using that very much in Florida, but perhaps they are. And then in late day, right around Memorial Day, Dr. Sri Rao will be presenting progressing towards performance-based specifications related to pavements. And we're currently working on topics that extend us through the summer and in the fall. It is a monthly program. So we do have a number of questions. I'd like to get into that right now. Next slide, please. So you see on slide 58, Mateo's email address. And if we don't get to your question, we have follow-up questions. Feel free to reach out to Mateo. He obviously is a pretty learned scholar on this particular topic. So now let me get into the questions. First of all, a question from Emmerly. How do ruts contribute to hydroplaning? Should the rut depth be added to the MTD thicknesses, or should it be subtracted from any MTC?
Yeah, thank you for your question. And if you remember when I was describing those factors that affect hydroplaning under the pavement and roadway geometry factors, we had the rut depth. And the rut depth has been added to the hydroplaning prediction tool, but it's only available under the continuous analysis option. So you will be required to input the rut in terms of a continuous file, as well as the crosslope and the grade. You will be asked for the rut. And the way the program deals with the rutting is it will calculate water depth due to rutting, which takes into account the crosslope as well. So if you're interested in using the rut depth, that's the way you will do it. You will use a continuous analysis and you will calculate the water depth due to rutting.
Great, thank you. I have a question. We have a question from Al. And Al's question is, in the first equation, and I believe he's referring to slide 24, that slide that you spent quite a bit of time on. What is the total slope S? Is it the sum or the product of the cross slope and the longitudinal slope?
All right, so the total slope, it's the combination of the cross slope and the grade. And if you look at the equation for the total slope, it's going to be the square root of the grade and the cross slope. So it's just the combination of those two. You take the square root and you elevate those two. You square those two and you sum them. That's what the total cross slope is going to be.
Okay, very good question though. We have a question from Jason, and Jason's question is, do we have reduction percentages in safety, lives saved, the reduction of injuries prevented and demonstrated by use of the FDOT hydroplaning tool?
That's a very good question. And yeah, one of the things that I'm trying to implement now is to follow up with the district engineers, because the normal workflow is that once we receive a request from the district engineer, we will look at and we will see if we have available data, available continuous data on that roadway. If we do have, we will run this analysis and we'll send a PDF report. If we don't have, we will go out there and collect the data and as well generate the report and provide some recommendations. But it's up to the district engineer to implement those mitigation strategies. And unfortunately, or the previous engineers that were in my position were not following up with the district engineers to know what has happened after we submit the report. So one of the things that I'm trying to implement is, after maybe 1 year or 2 years, follow up with the district engineer to see if our recommendations and the mitigation strategies have been effective to reduce the hydroplaning risk.
Okay, thank you. And I apologize, I'll likely mispronounce this person's name. Presmaslaw asked the question, you cannot avoid sections with very flat cross slopes and super elevation transition. What are the potential solutions for the HP risk in such situations? HP, of course, is hydroplaning.
Right. So yeah, when you cannot avoid those transition zones on the crosslope, the recommendation is to control the grade. And FDOT actually has a recommendation to have at least 0.5% of grade on these zones. So that will be what you could do. The other thing, the other strategies that you could do is maybe put some signs in there where you will prevent the drivers to increase the speed on those particular zones where you have increased risk of hydroplan.
Okay, wow, this is pretty popular. We've gotten quite a few questions. Next question, I'll continue with the questions until about 3 of. We have a question from Brian. Can the results be displayed on a KML or map to overlay with crash locations? Also, is it possible to back calculate cross slope for use in proposing maintenance treatments?
Very good question, thank you. And that allows me to mention that that's another of the functions that this tool has. You can output a KML file and you will be able to see the cross slope and the grade and the hydroplaning speed, the waterfall thickness on the actual road. So you can, as Brian said, overlap the waterfall thickness and hydroplaning speed with your crash diagram. And sorry, what was the other part of the question?
Yes, sure. Also, is it possible to back calculate cross slope for use in proposing maintenance treatments?
Yeah, so that's one of the things that we did on that example that I show you for the sensitivity analysis. So right here you have a section where you have almost no crosslope, and we ran the sensitivity analysis to find what the crosslope should be to have this drainage path not being at this long and to have the hydroplaning speed falling above the predicted driver speed. So yeah, you can use the sensitivity analysis option, for example, to back calculate what the crosslope should be to avoid all these problems right here.
We have a follow-up question from Jason, and I think it's a standalone question from his previous one. So his question is, how does the FDOT hydroplaning tool compare to other DOT tools used around the country? Does this place Florida as a lead state?
I was trying to do a research to see some other tools, and I didn't find so many. I know there is an NCHRP study, which is the 1555, and this project is led by Dr. Gerardo Flinch. And I saw that the approach that they are taking is different. Rather than calculating a hydroplaning speed, what they are doing is they are trying to calculate the hydroplaning potential. So pretty much is how feasible is that you will experience hydroplaning on that road. So that is a different approach, but I was trying to look for the report yesterday and I couldn't find it. So I'm not aware of all the other DOTs, all the other 49 states of what they are doing. I know that, for example, Texas has a different equation for waterfall thickness and hydroplaning speed, so I suspect that they may have another tool. But I think the good thing about this tool is that it is available for free and it is Excel-based, so if your department has a different equation that you could use, this is open source, so that you can input that equation and model the particular equation for your Department of Transportation.
Okay, we've just got a second ago another equation. Another question. Large drainage path always occurs at transition areas where the cross slope is 0. How long must this area be before it becomes a hydroplaning concern?
That was a very good question, and I had the question when I was starting to get into hydroplaning as well, and I asked one of the drainage engineer from Turnpike if he could provide me some insights on that. And you can see here there is a transition zone, and of course you're going to have the long drainage path, but this is not a transition zone. So when you have something like this, you should have controlled the crosslope differently. And about how long should be, that depends on several factors, the total length of the roadway and the geometry of the roadway. So it's not as easy as saying it shouldn't be longer than a tenth of a mile. but it will depend on the geometry conditions of the particular roadway.
Okay, perhaps a tough question, since you're so close to this particular tool, is what are the limitations of the FDOT tool currently?
Thank you. That's a very good question. And if you remember, this is the FDOT's enhanced hydroplaning prediction tool, and what has been enhanced is the tool itself, not the models. So we're using the same models for the water thickness and the hydroplaning speed. So the enhancement didn't represent any enhancement on the existing models, but only on the tool itself. So you may argue that you should be using a different equation for asphalt concrete than for PCC pavement. So or you could even say that you need a different equation for open graded and another for dense graded, but these are the limitations that the tool has so far.
Okay, one question, this may be our final one. It's a rather long one, so listen to me, and if I need to repeat it, Mateo, let me know.
Okay.
So it comes from Craig, and what about the effect of longitudinal grooving on concrete pavements? It takes water away from the surface, but also changes the drainage path.
Right. And
go ahead. And he clarifies a little bit, sorry. He's referring to diamond grooving as an enhanced saw cut and when concrete is started to polish.
Right. And that is actually going to be positive. If you look at this image again, this is one of those pavements where we had longitudinal grooving. What this is going to do is this is going to increase the texture. And if you remember when I was describing this presentation, the higher the texture depth, the lower the water thickness and the lower the drainage path is going to be. So in other words, if you increase the texture, it's going to be beneficial because you're going to reduce the water thickness and you're going to reduce the risk of hydroplaning as well. Okay,
and we've got one last question, then we've got a few more slides to close out. And this question is from Stephen. Would this tool still work in the northern US and the Canadian climates where climate is much colder and snow and sleet is a significant factor in weather-related crashes?
I mean, it's hard to answer that question without doing some sensitivity analysis. I will think that maybe if you're concerned about the temperature, you could maybe be using a different model instead of Galloway that doesn't take into account the temperature. So I will say first, before saying if it works or not, you'll have to try it with some of your data and see if it adjusts to your current crash data.
Okay, Mateo, would you please go to slide 58? We're almost done, folks. Just got a moment or two left. Thank you. Okay, very good. So just further clarification, all the webinar participants that have joined for the entire hour will be entitled to receive PDH certificate. We're not authorized to give CEU credits for this program. You'll also be able to receive a PDF file of today's presentation. Usually it takes us about 2 weeks to process that. And then if you do experience a problem after 2 weeks, just send an email to the address that you see here. And then finally, please, last slide. ARA is a national research and development company and consulting firm. We're always looking for great people. I'm on my 3rd career and my 8th year at ARA. After retiring from not-for-profit and the federal government. So if you're interested, we're always looking for valuable colleagues to join our team. Our motto is science and engineering for fun and profit. If you're interested in employment opportunities currently with ARA's transportation and infrastructure offices, please send a brief resume and your contact information to the address that you see on slide 60. I want to thank you all for joining today's program. Hopefully it met and exceeded your expectations. Mateo, thank you once again. Terrific delivery.